Hi, um, I will be releasing a series of videos covering the book Introduction to Robotic Analysis, Control and Applications from SAEED B. NIKU. So, this is the book that we will be covering Introduction to Robotics which is from SAEED B. NIKU. It is a very good book for beginners and experts, and we will be starting from chapter 2, which is kinematics of robots, robots, kinematics, position analysis. And in this chapter, we start learning how to write a point in a space and a vector in a space. Okay, so this book bringing this chapter starts with an image of a 4-bar structure in a closed loop. So let me draw a 4-bar structure in a closed loop. And that is a 1 degree of freedom. This is 1 degree of freedom structure. Let me draw this quickly. We have also a second illustration of a robot with a open loop. Okay, let me copy this and paste right here. And we also got a 4-bar, but now this is a robot as in moving, as is moving. This is A right here, this fixed point 01, 02, right here is B, and for this open loop, so that is the 1 degree of freedom. This is open, this is closed loop, closed loop. And this is open loop. Now, let me draw this, trying to make a effect, like it's moving. So if we apply some force on this bar, let's say we are applying a force right here, and if we apply this force, this this structure is going to move. So it was on this position and it changed for this position right here. Okay, repair, there is no fixed point uh, for now on this robot. um, any robot, every robot, it has a open loop structure mechanism. Any robot or a mechanism of open loop structure. In following the book, um, I'm a beginner on this subject, so I will be following the steps of the book. For this first mechanism of 4-bar, we have this equation. So let's write the equations of these mechanisms now. Easy. It's like a vector from O1 to A, from A to B, just like a vector. For from O1 to O2 and from O2 to B. Now for this open loop structure, we have O1 from A to B, and now as these are moving, as it is a open loop mechanism, now we have from B to C, which is equal O1 C. Okay, let me put this right here. um okay, we are at the very beginning of this lesson. um so let me read what the book tell to us. As you can see, if we have any deviation of the link AB right here, if we have any deviation, and let's say we are applying a force to this bar, and if we have any deviation to this link, the link um, O to B will be moving accordingly to this move. um, okay, so let's move on. We are on the topic. Let's go to the topic 2.3, which is conventions. Let's establish some conventions to start to write points in space and vectors in the space. Vectors. Again, we are establishing conventions to, because as we are throughout the book, we will use these conventions. So vectors, they are y, j, k, x, y, z, n, o, a, and p. Components of vectors. Later I will explain these conventions, these parameters, um, with more time. And x and y and z, ax, ay, an, az, sorry, you're going to have references, but I think for this first video is too much, and I will introduce this on the next coming up videos. We're going to have transformations, so but let's jump right to what matters on this chapter, which is learn how to write points and vectors in space. So the topic 2.4, which is a matrix representation, he brings that a matrix can be used to represent points, vectors, references, translations, rotations, transformations, um, as well objects and other kinematics objects. And on the topic 2.4.1, which is representation of a point in space. So a point B let's start drawing the axis. So that is the z-axis, x-axis, y-axis, and now we have the component of vectors, and a point B in space. And we can write this point B this way, as a combination of the three coordinates relative to a reference system. And believe it or not, a vector can be represented in the same way. Okay, so in the same way that you represent a vector, you can represent in the same way that you represent a point, you can represent a vector in a space. Now, these three components of the vector also can be written in the matrix form, and is this way. And this representation can be modified to also include a factor of scale W. So Bx, By, Bz, and W, and Bx, By, Bz are divided by this factor, this scale factor W, to be transformed back to Ax, By, and Cz. this way, so we can get ax back dividing bx by the scale factor w, and so on and so forth. W can be any number, and as it varies, it can get any value, and this change the size of the vector. Now let's solve some exercise, and so we can finish the video, and I hope the coming up videos can be also useful in some way for you. Okay, so this exercise give us a vector p, which is written as a combination of y, j, and k, and it asks for us to express this vector in the form of a matrix, but he asks to do this on the letter B with a factor W equal to, and that's easy. We have learned already how to do this right here. So now you know how to represent a point or a vector in a space this way or on this matrix way. Six, 10, 4, and 2, which is the scale factor. Is 3 multiplied by 2 is 5 multiplied by 2, and 2 multiplied by 2. And on the letter B, it asks for us to describe this in a direction as a unit vector. So first we need to normalize the length of the vector to be equal 1, and to do this, each component of the vector are divided by the square root of the sum of the squares of the first 3 components. of the three components. So the normalized vector is lambda, and is the sum of the square of the three elements. So that's how you normalize a vector. Okay. And that is equal to just substituting the values three, 5, 2, and we are left, and that is equal 6.16. We are not finished yet. We on the process of normalize this vector, and now to normalize, doing for each component, px is equal the value of px divided by the value of lambda that we just have got. So by is n px. Okay, what you're gonna do is divide the value of 5 for easy. Okay. And this is the unit vector. And now, as I was saying, when we normalize the length of a vector to be equal 1, we can do this now. This happens when we normalize a vector to be equal 1, which is a formality. Okay. And I think we still have time to do one more exercise. Okay, let's see the exercise, the example 2.2, and it says a vector B, it has a length of 5 units and is in the direction of a vector Q. Describe it below. So we have this unit vector Q, which is equal, it's represented on this matrix, and this component is not given, and we have to find this component QZ, and without this component we cannot know what P or. So as we have learned right here, we can find any of these terms by doing the normalization and equaling to 1 right here. Exactly. Let me drag this, let me copy this and paste right here. So we have to find this term QZ, and without it we cannot find the vector P. We want to find the vector P. Move it from units of this direction, 5 units of this direction. So if we got these components and applying on this formula to normalize the vector, if we do this square and this, we're going to obtain the following values. That is equal, and this square is equal to so this way we can find Q square Z. Okay, now extracting the square root on the both sides of the equation. This way. So we eliminate the square root on this side of the equation. So is the sum of this which is equal plus q squared z equal 1, q squared z is equal to 1 minus 0.448, and we find this component right here. Subtracting the square root of 0.552 is equal okay. Now we can write the q, the unit vector and the exercise say that b, which is the vector that we wanted to find, is on a direction of 5 units of the direction of this unit vector. So we just have to multiply this vector 5 units, so we find the vector b. And this is the scale factor, which is cannot be 0, of course. Okay, that's it. I hope that you could understand what I tried to explain, and hopefully which is my goal is to cover the whole book in the series of video that I wanted to release. And that's it. Hope you like it. Thank you.